Hello everyone, welcome to today's session. So this session we will be dealing with the topic enzymes. As you already have completed this topic earlier in the previous classes, so just we will brief regarding this topic today. So what are the enzymes? Enzymes are the biocatalyst that speeds up the metabolic reactions that occur in the body. Biocatalyst, here catalysts are nothing but the molecules that alter the rate of reaction. So these enzymes work in the biological systems, hence these are known as biocatalysts. So properties of enzymes are, most of the enzymes are proteins. That is, as we know already, proteins are made up of amino acids, and these amino acids are arranged in different 3D patterns, namely primary structure, secondary structure, tertiary structure and quaternary structure. So these structure of proteins is very important to maintain the activity of enzyme as well as to maintain the proper shape and structure of an enzyme. So if there is any change in this structure of the enzyme or property of this enzyme, the enzymes may lose their catalytic activity. Next is regarding the cofactors. Enzymes require cofactors for their activity. So these cofactors may be either inorganic ions like iron, magnesium or manganese, or these may be organic molecules like biocytin and coenzyme A. So these cofactors, either inorganic ion or organic molecules, these are loosely bound to the enzymes. So these cofactors, if they are tightly bound to the enzymes, then they are known as prosthetic groups. These prosthetic groups are non-proteinous in nature. So holoenzyme. So now this holoenzyme is a complete enzyme, that is enzyme with the active site along with the coenzyme. So you can see this is an enzyme and this is a non-proteinous coenzyme. So these coenzymes are non-proteinous molecules that are bound to the enzyme. So this whole is known as complete enzyme. That is the enzyme along with the active site and bound to the non-proteinous group is known as complete enzyme. So such enzymes are known as holoenzyme. So next is apoenzyme. So these apoenzymes are proteinous part of the holoenzyme. That is this. This is the protein part of the holoenzyme. This is non-protein part and this is a protein part of the holoenzyme. Next property is active site. So these active sites are special pockets or cleft of the amino acid that forms 3D surface complementary to the substrate. So you can see in this image here there is an active site and the blue color is a substrate. So these active sites are complementary to the substrate molecules. Next is catalytic power. Catalytic power is nothing but catalytic power can be defined in terms of turnover number. So turnover number is number of molecules of a substrate converted into product per enzyme molecule per second. Next, enzymes are highly specific in their activity. This specificity is maintained because of presence of active sites. These active sites are complementary only to the substrate. That is, specific substrate molecules comes and bind to the specific enzyme at their specific active site. So for this reason, enzymes are highly specific in their activity. Next is nomenclature. We had seen that nomenclature of enzymes can be divided into recommended names as well as systemic names. These recommended names are commonly used and they do not define exactly the activity of enzymes. But the systemic names, these systemic names have been derived or defined by International Union of Biochemistry and Molecular Biology. So this international board has divided enzymes into 6 classes as follows: as oxidoreductase, transferase, hydrolase, lyase, isomerase and ligase. So you can see in this image different classifications of enzymes based on their nature. Oxidoreductase, so these enzymes carry out oxidoreduction reactions or redox reactions. So example for this class is lactate dehydrogenase. Next is transferase enzymes. So the name indicates that they transfer a group of substances or group of molecules from one substance to another substance. So here you can clearly see there is a transfer of methyl hydroxyl groups. There is transfer of methyl hydroxyl group from the serine molecule to tetrahydrofolate. This THF is tetrahydrofolate. Next class of enzyme is hydrolase. So as the name indicate, hydrolysis, that is addition of water molecule and lysis of this urea molecule. Addition of water molecule and breakdown or lysis of the urea molecule to form carbon dioxide and ammonia. So this is the class of hydrolase. Next comes class of lyase. So these lyases and ligases. So don't get confused between lyases and ligases. Lyases are the class of enzymes that are responsible for breakage of bonds. You can see cleavage or breakage of bonds, while ligases are the class of enzymes that are responsible for formation of bonds. You can see a formation of bonds and cleavage of bonds. So lyases are the enzymes that cleaves the bond, while ligases are the enzymes that forms the bond. So here example for this is pyruvate decarboxylase, that is it breaks the bond and removes carbon dioxide molecules. So pyruvate is converted into acetaldehyde with loss of carbon dioxide molecule, while in case of ligases the carbon dioxide molecule is being added to the pyruvate. So here there is a bond formation between carbon dioxide and pyruvate that results in the formation of oxaloacetate. The enzyme responsible for this is pyruvate carboxylase. Next class of enzyme is isomerase. So isomers, we all know isomers are the substances that have similar molecular formula but different structural formulas. So here we can clearly see methylmalonyl coenzyme A and succinyl coenzyme. These both have similar molecular formula, but only difference is presence of position of this carbonyl group. Here you can see the position of carbonyl group is changed. So these enzymes are responsible for change of carbonyl group in this particular example. So this is regarding nomenclature of enzymes. So up till here we had learned. So the remaining topic we will learn today is factors that affect enzyme activity. So this enzyme activity is totally based on active sites, as we had already discussed in properties of the enzymes, that active sites is major for defining the enzyme activity. So what all are the factors that define enzyme activity? So here you can see enzyme plus substrate that leads to formation of an enzyme substrate complex. Here you can see enzyme plus substrate that forms enzyme substrate complex. This in turn forms enzyme and product. So now the important factors will be concentration of enzyme, concentration of substrate, concentration of product. Other factors that come into account is temperature and pH. So overall the rate of the reaction or activity or rate of enzyme catalysis is dependent on concentration of substrate, concentration of enzyme, concentration of product, temperature and pH. So individually we will learn how all these factors are responsible for maintaining the enzyme activity. So first we will see substrate concentration. How does it affect substrate concentration affecting enzyme activity? So if we take example enzyme and substrate converted into product. So here if we see, if there are 50 molecules of substrate and there are 60 molecules of enzymes, but the product form will be only 50 because substrate concentration is only 50. So altering the substrate concentration alters the product concentration. Also this substrate. So now, altering the rate of the reaction alters the product concentration. So rate of this enzyme increases. Rate of reaction increases as substrate concentration increases. Rate of reaction increases as substrate concentration. Next comes enzyme concentration. Second is enzyme concentration. Again, similarly we can see here example, if there are enzyme 60 molecules and substrate 50 molecules, but product formed is only 50. So altering the enzyme concentration also alters the rate of reaction. Altering the enzyme concentration also alters the rate of reaction. Here if we see, if we increase, another example we can take is product. If there are 50 molecules of substrate and only 40 molecules of enzymes, so product formed will be only 40. This is because only 40 molecules of the substrate will go and bind to the 40 molecules of enzymes. So resultant product will be only 40 molecules. If we want to increase the rate of the reaction, we have to increase the concentration of enzyme as well. So next is product concentration. Product concentration. So here again same example, enzyme plus substrate and product. So there are 50 and this is 40, so resultant will be 40. So now these 40 molecules, are obtained from 50 substrate molecules and 40 enzyme molecules. So now the reaction can be said to be saturated, because most of the substrate is converted into product. So now as the product concentration is high, so if we remove this product from this reaction, if we remove all the product from this reaction, so what happens? Enzyme plus substrate, initially it forms enzyme substrate complex, then only it will form enzyme and product. So if we remove this product, there will be more amount of enzyme substrate complex. So more and more amount of enzyme substrate complex will get converted into enzyme and product. That means the remaining 10 molecules of substrate will also be converted into product. That is, we will get 100% product. If we remove the product from the reaction, then only the remaining 10 of the substrate will go and bind to the enzyme and form the product, remaining 10 products. Also, this product concentration affects this enzyme activity as well. You can see A to B, B to C. So for this reaction A to B, let us consider E1 enzyme is responsible, and let us consider from B to C, E2 enzyme is responsible. So now this C, sometimes it tries to inhibit. This sign represents inhibition. So this C product will inhibit the enzyme E1. So in order to stop this reaction, that is stop inhibition of E1, if this E1 is inhibited, there is less amount of B, that is A will not be converted into B, and similarly B will not converted into C. So in order to inhibit this reaction, that is inhibition of binding of C to E1, this C should not interact with E1, so we have to remove this from the reaction. We have to remove the product formed from the reaction. So as soon as we remove this reaction will not proceed, so we will get more B and more amount of C. So we have to go on decreasing the concentration of C in order to prevent inhibition of enzyme. So product concentration is also important in order to prevent inhibition of enzyme as well as to increase maximal conversion of substrate into product. Next factor is temperature. Temperature. So as we know, enzymes are made up of proteins, and proteins in turn are made up of amino acids. So these proteins, they maintain 3D structure for activity. They have 3D structure that is responsible for maintaining enzyme activity. So when we heat or when we increase the temperature, so this 3D structure becomes loose. That is denaturation. That is denaturation. This denaturation leads to loss of enzyme activity. Loss of enzyme activity. So if there is increase in the temperature beyond limit, the 3D structure of the protein is lost. That is, the protein is denatured. So this denaturation leads to loss of enzyme activity. So as enzyme activity is lost, there is no catalysis. There is no catalysis. So particular temperature is required for enzyme to maintain its catalytic activity. So as we know, our body temperature 37 degrees Celsius. So enzymes function between 35 to 40 degrees. So beyond this limit, enzymes are denatured and thus there is loss of enzyme. Next factor is pH. So this pH, we know the scale of pH 7, 14 and 0. So 0 to 7 is acidic while 7 to 14 is basic. So particular pH as again amino acids, proteins and enzymes. So these amino acids, they contain amino functionality as well as carboxyl functionality. So amino functionality basic and carboxyl functionality is acidic in nature. So particular pH, at particular pH, enzymes are very active. Enzymes are very active. Any change in this pH will cause denaturation of enzyme, denaturation of proteins, that will lead to loss of enzyme activity. That will lead to loss of enzyme activity. So maintenance of pH is also important for. You can see this graph wherein a reaction velocity is plotted against pH. So pepsin, it is an enzyme that is present in GIT. So you can see between 1 to 3 pH, the activity of pepsin is high. So beyond this 3 pH, there is decrease in the activity of pepsin. That is, the enzyme gets denatured. Because of that, the activity of enzyme is lost. Similarly, the blue colored graph, that is for trypsin. This is also an digestive enzyme that is highly active between pH 5 and 7. pH 5 and 7, the activity of enzyme is high, and beyond this pH range, the activity of enzyme is lost. Similarly, for alkaline phosphatase, as the name indicates, alkaline, it is active at alkaline pH, that is pH between 8 to 10. So you can see between pH 8 to 10, the activity of enzyme is highly active, and beyond this pH range, the activity decreases. So this is regarding the factors that affect enzyme activity. Let's see regarding Michaelis-Menten equation. So this Michaelis-Menten equation is important to define quantitative relationship between substrate concentration as well as rate of reaction. The factors, or whatever we see define only qualitative relationship, that is whether the reaction rate will increase or decrease, but to what extent it will increase or decrease is defined by this Michaelis-Menten equation. So this Michaelis-Menten equation, as we can see again, enzyme and substrate, that forms enzyme substrate complex. So this forward reaction is denoted by equation K1. This forward reaction is denoted by K1, while the backward reaction, that is degradation of this enzyme substrate complex to enzyme and substrate, is defined by K minus 1. Also, ES will lead to formation of enzyme and product. So this is defined by K2. So overall reaction is E plus S gives ES, that will in turn lead to formation of E and P, that is enzyme and product. So this second step, that is ES conversion to E plus P, is a rate limiting step and slow reaction. As it is slow reaction and a rate limiting step, this is very important to define Michaelis-Menten equation. So you can see S is the substrate, E is the enzyme, ES is enzyme substrate complex, and P is the product. While K1, that is this, K minus 1 and K2 are rate constants. So now we will see how to derive this Michaelis-Menten. This is the final equation. V naught is equals to V max into S divided by Km plus S, where V naught is initial reaction velocity, V max is maximum velocity, Km is Michaelis constant, and S is substrate concentration. We will see how to derive this V naught is equals to V max S divided by Km plus S. So here we can see enzyme and substrate, that is converted into enzyme substrate complex. We will give this as reaction 1. Here you can see rate constants K1 and K minus 1. K1 is for forward reaction, while K minus is 1 for backward reaction. And also ES, that is enzyme substrate complex, is being converted into enzyme and product. The rate of the reaction is given by K2. This we can define as second equation. So as we all know that this second reaction is slow and is rate limiting in nature. So this, if we define its velocity, that is V naught, that is initial reaction velocity. Initial reaction velocity we have to define in terms of ES, because enzyme substrate complex is very important to define the overall reaction. So here V naught is equals to K2. K2 is nothing but rate constant of second reaction, because it is a slow reaction, so we have to take K2 as a constant. So V naught is equals to K2 into ES. So now we will define the rate of formation of ES. So you can see this is the rate of formation of ES. So here ES is formed. This ES is formed from enzyme and substrate, and the rate is defined by K1. So rate of formation of ES can be given as K1, that is this K1 into concentration of enzyme and concentration of substrate. Then rate of breakdown of ES. Now this ES can be broken down into two ways. ES can be broken down into two ways. One is either it can be converted into enzyme and product, that is one possibility, or second possibility is again it gets converted back to enzyme and substrate, that is second possibility. The rate of breakdown of ES can be given by either K2 or K minus 1. You can see here K minus 1, that is again reverting back into enzyme and substrate. Enzyme and substrate. So rate of breakdown of ES can be given either K2 or K1. Both the possibilities are possible. So K2 plus K minus 1 into ES. So if we combine both of these reactions as it is defined for ES, if we combine both the reaction, we can see here K1 into E into S is equals to K2 plus K minus 1 into ES. If we rearrange this reaction, we will get as E into S divided by ES K2 minus K minus 1 divided by K1. So after rearrangement, now this term can be defined by Km, wherein Km is equals to E into S divided by Es. So this whole term can be defined as Km, where Km is Michaelis constant. Km is defined as Michaelis constant. The whole term is defined as Km and the remaining equation remains same. If we assume that substrate concentration is much more higher than enzyme concentration, then the concentration of unbound enzyme, that is the concentration of free enzyme, will be equal to total enzyme concentration minus enzyme substrate complex. If we assume that the substrate concentration is much higher than enzyme, then the free enzyme concentration will be equal to total enzyme concentration minus enzyme substrate complex. So now if we substitute this equation 10 in equation 9, then we will get as Es is equals to Et minus Es into S by Km. So here you can see this is E equation we have substituted in this E equation. So this Km is equals to E minus S divided by S. We can also rearrange it into Es is equal to E into S as it is divided by Km. So now we have to substitute this E with E T minus Es. So instead of E we have written Et minus Es into S divided by Km. So after solving the equation 11, we will get equation 12, that is Es is equals to Et into S divided by Km whole divided by 1 plus S by Km. So again we have to solve this 12th equation. So you can see here Et into S by Km. Now we have to multiply this Km into 1. So we will get as Km plus S divided by Km. So if we bring this into numerical side, we get as Et into S divided by Km into, if we bring it to numerator, so this denominator will come upside, that is Km divided by Km plus S. Now this Km get cancelled, so the overall equation will be Et into S divided by Km plus S. This is 13th equation. So we also know that V0 is equals to K2 into Es. Now substituting the value of Es in this equation, we get V0 is equals to K2 into ETS divided by Km plus S. Now if we assume that enzyme is fully saturated with substrate, under such conditions Es will be equal to Et, that is enzyme substrate complex will be equal to total concentration of enzyme. So this, under such conditions, the rate of reaction will be maximum, that is V max. So this V max will be now equal to K2 into Et. So initially we had seen that V0 is equals to K2 into E S. So now this Es, we know that now this Es is equals to Et, that is total enzyme concentration, and initial velocity has changed to maximum velocity. Therefore Vmax will be equal to K2 into total enzyme concentration. So now substituting value of K2E2 as Vmax into this equation, we get V0 is equals to Vmax into S divided by Km plus S. You can see here K2ET has been substituted by Vmax value. So now this equation is our Michaelis-Menten equation. So finally we had derived Michaelis-Menten equation from enzyme plus substrate into enzyme substrate complex that was converted into enzyme and product. So this overall reaction can be quantitatively defined by Michaelis-Menten equation. Here you can see the Michaelis-Menten equation. The first graph, this is the blue colored line that defines Michaelis-Menten equation, that is hyperbolic in nature. So enzymes that follow Michaelis-Menten kinetics show hyperbolic equation. So here we can also see in the second graph at low substrate concentration. At low substrate concentration, the velocity of reaction is directly proportional to the substrate concentration. At low substrate concentration, at very low concentration, that is when substrate is much less than Km, the rate of the reaction is directly proportional to the substrate concentration, while at high concentration, here you can see, while at high concentration substrate concentration, the rate of the reaction is independent of the substrate concentration. Now we will see what are the significance of this Km and Vmax values. As we know, Km is a Michaelis constant and Vmax is maximum rate velocity. So this Km provides measure of substrate concentration required for the significant catalysis. Michaelis constant is dependent on substrate concentration in order to carry out effective catalysis. Here you can see Km is a measure of also strength of ES complex, enzyme substrate complex, means at high Km, that means if the Km value is high, there will be weak binding, that is enzyme substrate complex will be loosely bound, while at low Km values the enzyme substrate complex will be strongly binded. Here the significance is at high Km values, that is weak binding, this will lead to more formation of product because there is loose binding between the enzyme and substrate, but maximum interaction between enzyme and substrate. Weak binding defines maximum interaction, while strong binding defines less interaction. Therefore, high Km values, weak binding and more product formation. Low Km values, strong binding and less product formation. Also, this Vmax, that is rate velocity, maximum rate velocity, reveals the turnover number of an enzyme. As we already learned what is turnover number, that is number of substrate molecules converted into product per enzyme molecule per second. This is turnover number. So this Vmax reveals the turnover number of an enzyme. So we had seen that the Michaelis constant or this Michaelis-Menten equation gives hyperbolic type of curve. From this curve, maximum information cannot be gained, that is the concentration of a substrate or what is the rate of reaction cannot be exactly determined. In order to determine exact concentration of a substrate, how it affects the rate of the velocity, we have to turn this hyperbolic graph into straight line graph. You can see here straight line graph. So this kind of graph is defined by Lineweaver-Brook plot. This is known as Lineweaver-Brook plot. So this kind of plot can be obtained by inversing all the equations of Michaelis-Menten constant. The Michaelis-Menten equation, we had seen V naught is equals to Vmax into S divided by Km plus S. So if we invert or reverse is all the reaction, that is 1 by V naught is equals to 1 by Vmax into 1 whole divided by S Km plus S. So now this will be 1 by Vmax into this Km plus S will go into nominator side, that is Km plus S divided by S. So if we try to further divided by Vmax into S, this is same, right? If we solve this now, so Km divided by Vmax into S plus S divided by Vmax into S, right? So if we again solve this, this will be 1 by V naught. So 1 by V naught will be Km divided by Vmax into 1 by S. This is same as this equation, plus this S and S will get cancelled. So we'll get 1 by Vmax. So you can see 1 by V naught is equals to Km by Vmax into 1 by S plus 1 by Vmax. So we already have learned that y is equals to mx plus c. So this equation gives a straight line, right? So here y is 1 by V naught, m is Km by Vmax, x is 1 by S, and c is 1 by Vmax. So in this graph we can clearly define y, that is 1 by V naught, x is 1 by S. Here you can see 1 by S, m, that is slope. We define m as slope, that is Km by Vmax. We define slope as Km by Vmax, and c, this is y-intercept. We define it as y-intercept, that is 1 by Vmax. So this is regarding Lineweaver-Brook plot. So this is all regarding today's session. So today's session we were able to define how enzyme and substrate interact with each other, how their enzyme substrate complex is formed, how this enzyme substrate complex is converted into enzyme and products, and different properties of enzymes that affect enzyme activity. Then we classified and we defined a nomenclature for enzymes, and also we see how the temperature, pH, concentration of substrate, concentration of enzyme affects the kinetics of the reaction. And also we derived Michaelis-Menten equation, which is a quantitative relationship between substrate concentration and reaction rate. And also we turned this Michaelis-Menten equation, that is hyperbolic equation, into a straight line by using Lineweaver-Brook plot. So thank you for this session.